Hello everyone, in this video I will discuss Z transforms in signal processing and explain this code step by step to show how Z transform help us analyze discrete time signal in the Z domain. First, I import NumPy for numerical computation, Matplotlib for plotting, and SymP for symbolic mathematics, which allow us to represent Z transform expressions symbolically instead of just numerically. Next, I define symbolic variables z and n, where z represents the complex frequency variable and n represent the discrete time index, which is required when working with z transforms. After that, I introduce two fundamental signals used in signal processing: the unit step function u of n and the impulse function delta n. I explicitly print their known z transform formulas based on standard z transform tables. The unit step function u of n has a transform of x of z equals z over z minus 1 with a region of convergence absolute z is greater than 1, while the impulse function delta of n has a z transform of x of z equals to 1. These are basic but very important results because many complex signals can be built from these elementary signals. Next, I assign the z transform expression to variables so they can be reused later in the code. I then demonstrate the inverse Z transform manually by referring to Z transform pairs from the table. For U of n, since the form matches Z over Z minus A, we identify A equals to 1, which directly gives us U of n as the inverse Z transform. For delta n, the inverse Z transform is 1 is simply delta n, confirming the time domain representation. To verify this numerically, I generate discrete values of n from 0 to 9 and create arrays representing u of n and delta n. The unit step appears all ones starting from n equals to 0, while the impulse has a value of 1 only at n equals to 0, and the 0 elsewhere, which confirms their expected behavior in the time domain. Next, I move to visualization in the z domain. I generate complex z values using polar coordinates where z equals to re times j theta. These allow us to analyze how the z transform behaves for different radii and angles in the complex plane. I then compute the z transform values numerically for both u of n and delta n over these z values. Finally, I plot the magnitude and the phase responses. The first row shows the magnitude and phase of z transform of u of n for two different radii, r equals to 0.5 and r equals to 1.5, which helps illustrate how the z transform behaves inside and outside the region of convergence. The second row shows the magnitude and phase of z transform of delta n, where we observe that the magnitude remains constant and the phase is 0 regardless of the radius because z transform of an impulse is equals to 1. Interpreting the output, we can see the unit step function produces a z transform whose magnitude and phase vary with z, reflecting the presence of a pole as z equals to 1, while the impulse function produces a flat magnitude and zero phase, indicating that no poles are zeros. This clearly demonstrates of how Z transform provide insight into system behavior, stability, and frequency characteristic in discrete time signal processing.